So we're going to have a look at chemical equilibrium today. This is Unit 9 in our course, Chapter 15 in your texts. We're looking to look at this particular reaction. We have N2O4 going to 2NO2 gas, a very simple chemical process. And we're going to basically start using what we did in kinetics to sort of understand this. So first of all, this particular reaction is governed by this rate law. N2O4. So the rate of reaction is equal to N2O4. We're going to assume a single step mechanism here. Now, what happens is one molecule will form, these break up into two, forming two molecules of NO2. But just as likely, we're going to see two molecules of NO2 recombine to form one molecule of N2O4. So we write 2NO2 gas goes to N2O4 gas. So with that particular chemical process, that would of course have a rate as well. And we've seen this a little bit in our course already. Basically looking at unimolecular steps or mechanisms. So assuming these are just elementary reactions, that's fine. We're going to go from one molecule to two or two to one. Basically, we end up with the forward reaction or the reverse reaction. Now, because they're both happening at the same time, we actually normally write N2O4 and put a two-way arrow to 2NO2, and that's still a gas, and that's still a gas. And where we start getting into definitions here is that equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction, or these two rate laws are equal. So we write the forward reaction K N2O4, and we say that that's equal to K, let's call this forward and reverse, NO2 squared. So equilibrium is established when the forward and reverse reactions have the same rate. So what we're going to do is we're just going to isolate terms, and I'm going to solve for K forward over K reverse is equal to the product over the reactant. So K forward is equals K reverse. And it's kind of inconvenient to write that. So we're just going to write a capital K, and we're going to call it KEQ, or the equilibrium constant. The equilibrium constant is defined as the ratio of products to reactants, the concentration in this case in moles per liter, raised to their stoichiometric coefficients. So generally what we're going to do is we're going to have a reaction where we have a general form. So A plus B gives me C plus D, where the small letters or lowercase letters are the stoichiometric coefficients. We say that KEQ, or in this case KC, the equilibrium concentration quotient, and then we have the equilibrium expression, which KEQ is general, KC is referring to moles per liter being used. We would write the concentration of the products raised to their coefficients over the concentration of the reactants raised to their coefficients, and this is called the general form. Basically all coming down to the fact that the forward reaction and reverse reactions have to have the exact same rate. So we can take some time and actually practice doing this when we take out this handout, which can be found on the website, or you were given it in class, called equilibrium expressions. So the first thing we're going to do is we're just going to write the equilibrium expressions for these particular reactions. So the first one is 2 moles of ozone going to 3 moles of oxygen gas. So we write Kc is equal to the concentration of the products raised to its coefficient, which is a 3, over the concentration of the reactants raised to its coefficient. We do the same thing with B. It's the concentration of NOCl raised to its power and we don't have to write ones obviously when we do this. And we can do the third one as well. It's the concentration of Ag and H3 2 plus 1. 1, so it's a coefficient of 1. I don't write anything. So we have equilibrium constants. Because there is a relationship here between concentration and partial pressures, for A and B anyway, where all of the species are gases, we can write a separate equilibrium expression. So I'm going to write this hopefully in red. And we're going to call this Kp. So this is the equilibrium constant with respect to partial pressures of the gases. It's written exactly the same way, but we don't use square brackets because they indicate concentration. So we're at the partial pressure of oxygen raised to its coefficient over the partial pressure of ozone raised to its coefficient. They look very, very similar, but they will not have exactly the same number because concentration and pressure are not the same number. We can relate the two of them, but and we'll do that in step 2. So same thing here, we have NOCl, partial pressure of NOCl squared over the partial pressure of NO squared, the partial pressure of chlorine to the first power, and those are all products, of course. Partial pressure is very, very useful when you're dealing with gases, especially if they want your answer in moles per liter, atmospheres. And then this is more useful when you're dealing with moles per liter, which is generally aqueous solutions. So the part C here, you'll notice that they're all aqueous. You can't use a partial pressure or Kp for that because it's not actually a gas. So what we have to do now is we have to actually look at what this number means. So once again, we have this particular reaction here. 2 moles of sulfur trioxide is in equilibrium with 2 moles of sulfur dioxide and oxygen. I notice we're all dealing with gases here, and we have the equilibrium constant with respect to concentration. So that would be with respect to the moles per liter. So what's up here in blue? We want to calculate Kp. But we do not have the volume of the container. We just don't have enough information directly to do it by turning concentrations into pressure, at least not easily. So we have this equation here, and it says that the equilibrium constant with respect to pressure, Kp, is equal to Kc times the gas constant, that's the 0.08206, times the temperature, the absolute temperature, so that you have to use Kelvin, and RT is raised to the power of the change in number of moles of gas, or delta N. So if you were to have a liquid or solid in the chemical equation, liquids and solids are not included in equilibrium expressions because their concentrations do not change. So you would not include those, though, in the change of moles. It's got to be the change of moles of gas because you are dealing with partial pressures. So we simply are going to write Kp is equal to Kc, so 4.08 times 10 to the negative 3. And you should have noticed at this point that there is no units with K. Technically, there would be some sort of unit with regards to concentration, but because they're changing so frequently depending on the chemical equation, we don't use them really at all. So the ideal gas, 206 liter atmosphere. Mole K. And again, it really doesn't matter to write the units in, I suppose, simply because whatever's left over is not going to be on the K. We're just not going to include it. Times 1000 K. And here's the only part that seems to catch people, is that it's got to be the change in moles of gas. In this case, it's not a big problem. So the change in moles of gas would be the number of moles of gases in the product. So 2 plus 1 is 3. Take away that in the reactant, so 2. So you're going to raise this to the first power, which makes this calculation a lot easier. So Kp in this case is equal to 0.334. Now this is incredibly helpful when you just need to go right to partial pressures and atmospheres. You can just go and use KP. Um, the benefit of doing it is just that you're saving yourself multiple concentration calculations, even if you do have the right information or enough information. So one of the things that we have to kind of get our heads around is converting KP and KC based on how the reaction is written. So because we have a two-way reaction, as we've talked about before, what's listed as a reactant versus what's listed as a product is kind of arbitrary because both reactions are taking place, both the forward and reverse. You could write it in the reverse way and still have the exact same situation going on. However, the equilibrium constant would change. So this particular process here is called the Haber process. So it's 2 moles of nitrogen plus 3 moles of hydrogen giving me 2 moles of NH3, and this is an equilibrium process. So we could write Kp, because it's asking for Kp, the partial pressure of NH3 over the partial pressure of N2 times the partial pressure of hydrogen gas raised to its coefficient. So we write our Kp expression. Well, that's for the reaction as written, the forward reaction, as some people say. If we were to write this with the reverse reaction, the what's on top and what's on bottom would have to flip, or in other words, you'd be writing the inverse. So if I were to write the reverse reaction, NH3 going to N2 plus H3, if I write the reverse reaction, then it's always going to be products over reactants. So I would have Kp, I'm just going to mark a little dash to show that it is the reverse, is equal to the partial pressure of nitrogen times the partial pressure of hydrogen, H2, for the partial pressure of NH3 raised to its coefficient. So these are exactly opposite. So we can easily say that Kp prime is equal to 1 over the forward. So very easily we can just take the inverse of that number, and when we do that we get a number of 230. Again, no units, and that's all we have to do. So when you are asked the Kp of the reverse and you're given the forward, it's very easy to find that particular number. So it can get a little bit more complicated than just taking the inverse, and sometimes we have the equilibrium constant for individual steps, and this is going to kind of look a little bit like Hess's law, which is what we did in Unit 5 with regards to enthalpy. However, the rules for how we add the constants are very different. So basically what we're trying to do here is we have two steps. We have an equilibrium process with hydrogen fluoride, or in this case it's actually hydrofluoric acid, but I'm going to H plus and the fluoride ion, and then we have acetic acid, not acetic acid, we have oxalic acid breaking into its ions of 2 moles of H plus and 1 mole of the oxalate ion. So basically, given those two known values, equilibrium concentrations, we should be able to figure out what this overall reaction's equilibrium constant is. And what we're doing is we're simply trying to figure it out in a way where we don't actually have to do a bunch of experiments, or in other words, just figure it out theoretically. So we're going to treat it very, very similar to what we did before. So the first thing we see HF in our first reaction, so let's call this reaction 1 and reaction 2 just to make our lives a little bit easier. So basically all I do is I take the approach of trying to basically adjust the first reaction to match what we see. So HF is a reactant and it's a reactant, but you'll notice that it's 2HF. So what I'm going to have to do here is actually double all the coefficients. So I'm going to multiply it all by 2. So 2, 2, and 2. Now, when we did this in Unit 5, we simply multiplied the constant or the enthalpy by 2, but that doesn't work here because of what we're dealing with. Because the coefficients are related to the exponent and not directly the species itself, you actually raise the equilibrium constant to the power. So since I doubled it, I'm going to raise it to the second power. If I had tripled it, I would have raised it to the third power, and so on. So I can simply do that calculation. It's very, very straightforward. 6.8 exponent 4 negative, and I'm just going to square it, and I get 4.624 times 10 to the negative 7. So I've just taken that into account. The next thing I have to worry about is that I have the oxalic acid on the product side, but up here it's on the reactant side. So that means that we're going to have to flip it. So I'm just going to flip this reaction, C2O4 plus H plus, to get 2 moles of that, and the oxalate ion. Ignoring the fact that I'm not putting in the states just to save a little bit of room. Basically, we reverse that, and we just did that in the previous page. So we know that we're just going to take the inverse of that reaction, or that number. So I write in 3.8 exponent 6 negative. So I'm going to take that number, and I am going to take the inverse of it. And that gives me 263,158. Not really worried about significant figures here. Now when I add up those two reactions, I will get the overall reaction. There's no need to actually show that step. It's something we've already done. However, Kc, or the new Kc, again, is not just the sum. When you've done individual steps like you would in this particular case, it is the product of the individual steps, not the sum. So we're going to write 4.624 times 10 to the negative 7 multiplied by 263,158. So if I had 5 steps, I would have 5 numbers listed as the product. So the new Kc value is equal to 0.122. And that is how we simply add them up. If we were to divide, then you would basically just have to do the exact opposite. In other words, remove the 2. So basically, it would just be essentially minus 2. But frequently, it's more multiplication than subtraction or divisions. In the equation. So very rarely are you going to be cutting reactions in half. The final part of this lesson is dealing with solids and liquids. So I've kind of alluded to earlier that we don't really include them in the equilibrium expressions. And there's a really simple reason. The concentration of a pure liquid or a solid doesn't really change. Whether you have 1,000 liters or 1 liter of water, the concentration of water at that temperature is fairly constant. So we don't really include, there's no point, it's just going to stay the same. So when you're doing these particular reactions, all you do is you leave those out. Just basically insert a 1, or in other words, don't write them. So for this one, we have a gas, a gas, a gas, and a liquid. So we're basically just not going to include water. And it's asking for Kc. So Kc is equal to the concentration of carbon monoxide. And we get that. Water, again, not included. It is a liquid. So basically the only thing that you are going to be putting into equilibrium expressions are things that are aqueous or AQ and things that are partial pressures or gases. For B, Kc is equal to, so I have a solid and I have a solid. So it's the concentration of CO2 raised to its coefficient over the concentration of CO raised to its coefficient. If you, for example, had all your reactants or all your products as a solid, you basically would have one. So in a situation where, let's say that this was dry ice, it was a solid, you basically would just have 1 over CO squared. And that's okay, that's fine.